Hello, everyone, and thanks for joining us. And welcome to our second talk of 2026 invited seminar series organized by IEEE Computer Society San Diego chapter. Today, we are excited to have Dr. Aniket Roy. Aniket recently earned his PhD degree in the Computer Science Department at Johns Hopkins University under the guidance of Bloomberg Distinguished Professor Ramachalapa. Prior to that, he did a master's from Indian Institute of Technology, Kharagpur. He was recognized with the Best Paper Award at IWDW 2016 and the Marcus Thomas Memorial Award for the Best Research Paper at the master's level. During PhD, he explored domains of few-shot learning, multimodal learning, diffusion models, LLM, LoRA, merging with publications in leading venues such as NeurIPS, ICCV, TMLR, VACV, CVPR, and also 3 US patents filed. During his PhD, he also gained industrial experience through multiple internships in Amazon, Qualcomm, Merrill, and SRI International. He was awarded as an Amazon Fellow from 2023 to 2024 at JHU and selected to participate in ICCV's 2025 and AAAI 2026 doctoral consortium. With that introduction, Dr. Roy, the floor is yours. Please take it away.
Thank you, Peters, for this introduction, and thank you for inviting me for this talk. It was really an honor to present my work here. And thanks everyone for joining. I know it is like I'm late here, but still I'll try to make the talk more interesting and more interactive so that if you have any questions, you can directly raise your hand and maybe ask that. So with that, I start my talk. It called Recent Advancements in Image Generation and Understanding. Myself, Aniket, as Priyas mentioned, I did my PhD from Johns Hopkins with Professor Ramachalapa, and I'll be joining NEC Lab soon. So this is the overview of the talk. I will start with some introduction and the motivation of my research. And then I'll present two of my recent work, DiffNat, which published in TMLR, and another is DuoLoRA, which published in ICCV. And then we'll go through some future directions and the question answers as well. So let me start with the evolution of image generation. Image generation has evolved a lot from past decades. So for example, before 2014, those are mostly handcrafted image generation method like Gaussian Mixture Models. From that, you can see the image generation qualities are not that great. So here's the example of MNIST generation. And you can see that those are not very good quality images and the resolution is also very small. Next on 2023 to 2013 to 14, here comes Variational Autoencoder, which improved the image quality quite a bit, but still far from what we are seeing right now. Then on 2014 onwards, here comes generative adversarial networks, popularly known as GANs, which improve the quality quite a bit. For example, here you can see the face generation qualities are pretty good. And that time it was actually a kind of rewarding model and how you can generate images efficiently. But there's some issue with how you can train the model because those GANs are very difficult to train due to instability issues. Then on 2020 onwards, here's come diffusion model. And you can see that diffusion model generate very naturalistic images. And it is very stable and has a good mathematical backbone. So right now, diffusion models are kind of state of the art for image generation. So a bit of background of how diffusion model works. As you can see here, the main idea is to add noise in the images till it becomes a total Gaussian noise. For example, this xt, you start with x0, you add noise in each time step till it became totally random Gaussian noise. And the idea or the goal is to learn a denoising autoencoder parameterized by p theta here, which intakes a noisy version of image and output a denoised version of the image. And finally, the goal is to reconstruct the image which is originally there. So this is a background of how diffusion model generally works, but there are much more different variants which I'll discuss again. So in this context, I am presenting our recent work called DiffNat, Improving Diffusion Image Quality Using Natural Image Statistics. Natural image statistics. So this is joint work with Maitreya, Anshul, Ketul, Jiang, and Professor Chelappa, and it published in TMLR recently. So now I'll give a brief overview of the work. What is the goal? What are the challenges? And what are the key novelties of our approach? So as I mentioned already, that the goal is to improve the image quality. And the challenges are that, as I have shown earlier, there is a different models like GMM, then VAEs, then GAN, then diffusion model. Instead of coming up with new model, can we do something which is more generic and can be applied universally? So that was the goal here. And the novelties are, we use kurtosis concentration property of natural images as prior. And using this prior, we propose a plug and play kurtosis concentration loss, which improve the image quality overall. And additionally, we also propose a perceptual guidance strategy, which increase the image quality even further. Now, what is kurtosis concentration property of natural images? Now, let me explain that. Suppose if you have a natural image and you do discrete wavelet transform with different bandpass filtered version of the images, you generate different bandpass version of the images, which are low frequency version, high frequency version, or combination of all of those versions. It has been noted, or it has been kind of observed, that the kurtosis is basically a fourth order moment. The kurtosis of the bandpass filtered version images tends to be constant for natural images. So this is the property which has been studied from early 80s or 90s, and the observation has been done that in the fourth order moment, the kurtosis values across the bandpass filter are constant. So this is the kurtosis concentration property. So now we try to understand why this property actually hold. It sounds interesting, but what is the intuition or mathematical reasoning behind that? So it has been earlier observed that the distribution of discrete wavelet transform filtered version of natural image follows a generalized Gaussian density function which of this form, where alpha, beta are some scaling parameter, and p of x is the density function of the discrete wavelet transform filtered natural images. Now, if we compute the kurtosis, the fourth order moment analytically, it boils down to some value which is which is independent of x, and it depends only the gamma function of these beta values. As I mentioned, that alpha beta scaling parameter, and since this kurtosis is independent of x, it is a kind of intuition. Okay, across fourth order moment, the kurtosis values are independent of x, and it has supposed to be constant. It also has empirically be observed for natural image, these beta values are relatively small, and therefore this value tends to be a constant. So this is the mathematical intuition or understanding why this property is actually working. Next, we use this property to propose a plug and play loss function. As I mentioned, the kurtosis concentration loss, which improve the image quality across multiple tasks or multiple method. So for example, Dream Booth is a very well-known method of personalized few shot fine-tuning tasks. The goal here is to, suppose if you have an image of this bag and you want to generate different version of this bag across different viewpoint or different background or different context. So in this case, what we observe that if we get the Dream Booth generated images, the kurtosis span, which I already mentioned, is quite high, and the image quality is there are some inconsistency or lower quality image. But when we add the kurtosis loss, which I'm going to present next, the image quality improves and the kurtosis span also reduce. So yeah, this is the context of the kurtosis loss. Next, I'm going to explain how the kurtosis loss is actually used in any diffusion-based pipeline or how it is a plug-and-play loss function. So suppose for your task, you have some input images, for example, this bunch of cats, and based on your task, you have some additional task-specific input. It could be images, it could be text, it could be combination of both, or it could be none. Now, the task in hand, which we kind of deal with, was like text to image generation or image to image generation or unconditional image generation and so and so. For each of the tasks, we also use multiple method. Like for text to image generation, we use dream booth, we use custom diffusion, which are like different way of dealing the problem. For image to image generation, you also use guided diffusion, we use Kara's diffusion, which are different approach for doing this task. And as I already mentioned, the basics of diffusion model, what it does on the input images, it try to add noise till it becomes totally random noise. And the goal is to reconstruct from the denoised version, from the noisy version of the image, what actually the ground truth is. So for diffusion model, generally the goal is to try to minimize the reconstruction objective. It is also known as diffusion loss, that if you have from the input images and the reconstructed images, you need to minimize the L1 or L2 distance, something like that. And for each of the tasks, it could be text to image generation, image to image generation, or any task. It might have some approach specific task loss, which we term as L task. So this is approach specific. So we are not touching this loss. It should be as it is. Now I'm going to explain how this kurtosis loss is used. So the kurtosis loss is actually applied on the reconstructed images during each of the denoising iteration. And the method is very simple. On the reconstructed images, you do different bandpass filtered version of the images, like discrete Weber transform bandpass version of the image with different filter banks presented as C1, C2, Cn. And you just minimize the maximum and minimum kurtosis difference. So that is the kurtosis loss, which is very simple to use. And that's why it's very easy to apply to any kind of task or any kind of pipeline. So yeah, so this is the kurtosis loss, where this is the difference between the maximum and minimum kurtosis values, which could be applied on the reconstructed images. But here one thing to notice that in diffusion, recent diffusion models are not necessarily a image-based diffusion model. It could be a latent-based diffusion model where the denoising happens in the latent space when you transform the images from a latent space and do the denoising on the latent space. If you try to apply the kurtosis loss on the latent diffusion model, then from the latent space, you have to reconstruct it in the image space and add this image loss, like kurtosis loss. Because here our intuition or idea is that this is a prior of natural image. So this loss has to be applied to the natural image space, not in the latent space. Yeah. Do anyone have any questions on this?
I do have a question regarding this loss. So you're essentially trying to create different versions of that reconstructed image by applying filters. And since the kurtosis concentration should be irrespective of the image, you're trying to just minimize this range. Is that
Yeah.
the intuition?
Yes, yes. Yeah.
Okay.
So we want to make sure that when the reconstructed images are generated, so the reconstructed images should be natural. So therefore, we add the reconstruction of on the reconstructed objective, we try to minimize the kurtosis span.
Mhm. Yeah, yeah. Okay, thanks.
Yeah, I do have another question. I'm not
Yeah.
familiar with the term natural image. When you say natural, is the
Mhm.
detail of the object texture detail, or is the lighting, or what is that definition of a natural image?
Natural image, by natural image, I mean to have, suppose the image which is captured from natural scenes, uh like it could be it could have this texture or any kind of natural details. So basically, if you collect a data set from natural images by taking the pictures, those we can see tell as natural images which are have like natural scene. But so for unnatural scene, you can say that, like, suppose we have cartoonish image or like some other this kind of variation image, like synthetic images, those are not natural. So by natural, I'm meaning which is, yeah, if you click a picture, that thing, the
So
details
is
you can
it the
see.
outdoor picture or inside?
It could be outdoor, inside, everywhere, anything. Because that's, for example, this cat and everything, these are indoor object or indoor animals, this thing. And it could be also outdoor stuff. So it has been observed that for natural images, if you have, it could be indoor, outdoor, everything, this kurtosis statistics hold.
Okay, thank you.
Mhm. Yeah, and that's why we call this natural image prior, because this is a prior for natural image. If your goal is to like generate something synthetic image, but suppose cartoonish or some anime, this kind of stuff, then it might not a good prior for that case. Yeah. Is there any questions? Any more questions? Yeah. If not, then maybe I can just move
Yeah.
to the next part. Okay. Yeah. So yeah. So now we propose this kurtosis concentration loss to improve the image quality, but then we became more greedy. Okay, can we improve even further to do something on top of this kurtosis concentration loss? And specifically, if we can design some inference time guidance strategy which could improve the quality even further. So apparently we can. We call it a perceptual guidance, which improve the image quality even further with the guide of kurtosis concentration loss. Uh, Now, for image generation, for in diffusion literature, classifier free guidance is a well-known concept where if you have where you want to improve the quality of the image without training the model. Suppose if you already have pre-trained model, using the pre-trained model, how you can improve the image quality without even further. So the idea here is to uh, generate some, like, suppose our goal is to generate alien in the beach. This is the prompt. Now I have some score by score function. By score, I mean that prediction of a model with respect to some prompt, specific prompt or conditional prompt or unconditional prompt. So suppose we have a unconditional score where it shows what is the prediction of the image on the beach. We call it unconditional score. Now, if our condition is alien, we want to have the alien in the beach. So the conditional score is to be like this, epsilon theta of xt ct. Now, if I want to generate an image with the prompt that alien in the beach, generally the conditional score are uh, combined in this way. So it starts with a unconditional score and it guides toward a conditional score. So this is similar to the contrastive learning where you start from a negative and try to push towards the positive. So you can see the similar analogy here. So you are starting with a unconditional score. You are guiding your diffusion trajectory toward a conditional score, so that your generated image is more aligned toward the condition. Here the text condition. So this is called classifier free guidance, which is used in diffusion literature. But similar to classifier free guidance, we want to propose, can we modify this somehow to use perceptual guidance or use the perceptual loss we have already proposed. So how this work, we call perceptual guidance. So suppose we have a score of the base model, where the model is already used without the kurtosis loss. And that, since we know that kurtosis loss improve the quality, so the base model have bit lower quality image or low quality image generation. Next, we have a score, which is a prediction, where the score is through the model which is trained with the kurtosis loss. Like it shows the score of the perceptual model with kurtosis loss. Now, similar to the idea of classification guidance, what we can do, we can just combine these scores in this way that it starts with a low quality image and it guides toward a better quality image. As you can see, it starts from this and it guides toward a better quality image. So it actually, what it does, it guides the diffusion trajectory during inference phase toward a better quality image. So I have this low quality image, I have a bit better quality image. Using combining these two quality images or their predictions or scores, we can combine an even better quality image, which looks more close to this good quality image and go away from the lower quality image. So this is the idea called perceptual guidance. Here we are using the loss in the inference stage to improve the image quality even further. Yeah. Do you have any questions on this?
Actually, I do. So,
Mm.
what you're discussing here is that during the inference steps associated with the diffusion model, as you're going through those iterations, you're trying to have another model to provide some guidance for those diffusion steps.
Yes, yes.
And that secondary model is the one that's trained
With kurtosis
kurtosis.
loss. Yes, yes.
Oh, okay.
Yeah. So basically you have a base model which is trained without the kurtosis loss. And there is another model which is trained with the kurtosis loss. And with this course or prediction which you already have, you don't need the model. You don't need to retain the model. But with the trained model, with the two trained model, basically, and the predictions, basically, you can combine the scores so that it could create even far better quality images.
Oh, I see. So that second image, the one in between, is the one that's generated by the model which was trained by kurtosis.
Yeah.
So there is some synergy forming between the two models. Is that what you're saying?
Yeah, exactly. So basically this is a predict. So you can see that theta b is the prediction of the without the kurtosis model, and theta p is with the kurtosis model. So then you combine the prediction or the scores so that it can like generate better quality image without any additional training, just combining the scores.
I see. Okay.
Yeah, that's
Thanks.
why yeah,
Mm.
you're saying.
How do you ensure that it's better than both of them?
Yeah, so that's how we ensure, because that is the idea of like the basically it is obviously, so for this equation you can see it is somehow in the range of theta b to theta p in this quality. And with this guidance scale, basically you can kind of choose how you want to align with those base model and the perceptual model. So we find out if suppose that the guidance scale is 0, that means you are getting only the base model, and guidance scale is 1, that means you are getting the predicted model, like these things. But when you combine those two, you can have a full spectrum. Using that, you can generate better quality images. And that is a kind of like so that is one good understanding of like how classification guidance works and the linearity of the scores this work.
Well, I have a question. Can you repeat? How do you define better quality? Is a human can be maybe someone will say the second image is better quality. Then this is a different value of that. But how is it someone decide that it's better?
Yeah. I have the like in the next slides onwards, I have the quality metrics and quantitative metrics, and also human study. So I can show next. So basically we are using the standard metrics, FID score, PSNR, SSIM, and with these metrics we kind of understand how these are kind of how the quality is changing. Does that answer your question?
Yes, yes.
Okay, yeah. Next slide is on the results, where actually show how we quantify the improved quality and how we did this analysis on top of that. Yeah, on that related that. Okay, maybe let me go to the next slide then. Okay, so that's the thing of with perceptual guidance strategy, that so the classification guidance has some kind of disadvantage, that the goal of classification guidance is to align with the text condition, not necessarily the image quality. The image quality improves as a byproduct, and it can't be applied to unconditional model. But compared to that, perceptual guidance strategy, our goal is to guide toward better quality, because we are starting with a low quality image and guiding toward a better quality image. And it could be applied to any unconditional model as well. And additionally, it is complementary to classification guidance. On top of the classification guidance, we also can add perceptual guidance. Okay, yeah. Next, I go to the qualitative results. So this is the task for image super resolution. For example, you can see the input images are like low quality, low resolution image, and the goal is to generate better quality image from the diffusion model. And this is the example from guided diffusion model. So we can see that when you add the kurtosis loss and the perceptual guidance strategy, the image quality improves. In the sense, we have noticed that in some cases, there are visible improvement or visible artifact reduction. For example, here you can see with the guided diffusion model, the eye regions are a bit blurry, but when we add the kurtosis loss, it actually improves the eye region. And when we add the perceptual guidance strategy, the eye region improves even further compared to the baseline or the ground truth. So those are the qualitative results which we can show, and this is the quantitative results. So for super resolution tasks, these are the image quality metrics, which are pretty well known for the tasks like FID score, PSNR, SSIM, and music score. And also image diversity, because we don't want the image, all image to be the same. So we want to also want LPIP's diversity, which is a measure to which is a measure to uh, identify how diverse the images are, generated images are. So we notice that when we add the kurtosis loss and perceptual guidance strategy on the guided diffusion benchmark, with FID reduces, which is good, and PSNR, SSIA music score improves. And similarly for latent diffusion models also, we find out the same trend, which verifies that the quality is actually improving. And generally, when it has been noticed that whenever image quality improves, the diversity is compromised. But here we have noticed that the diversity is also not compromising, because we try to understand. Our intuition is that this kurtosis loss is also act as a regularizer during the diffusion denoising process. That's why the diversity is also not compromised here. Next, we also did some perceptual evaluation that so here in the guided diffusion generated image models, we try to locate where are there unnatural artifacts with the perceptual artifact ratio, which is proposed in some standard paper. So we notice that when we add the kurtosis loss, the perceptual artifacts are reduced, both qualitatively and quantitatively. For quantitative analysis, we kind of measure the perceptual artifact ratio, which is the average perceptual artifact ratio across the dataset. And we notice that when we add the kurtosis loss, the perceptual artifact ratio reduces. So that implies that the generated images are more natural. And additionally, that these perceptual metrics sometimes are not very reliable or not very Yeah, perfect. So that's why it is preferred to have human studies. For human studies, we did like human study with Amazon Mechanical Turkers. And we did this Amazon Mechanical Turkers with 50 unbiased and unknown observers and asked them questions that, okay, given this image and the DiffNat generated image and other baseline images, which do you prefer based on naturalness, good quality, everything? And we noticed that humans also prefer DiffNat generated images compared to baselines. So yeah, so that did actually concludes the DiffNat work. If you have any questions, please let me know.
I think that the last one, the artifact.
Yeah.
What is the scientific reason? Why there's some object there is not natural. Say if AI generate 6 fingers,
Mm-hmm.
3 hands, are they natural or are they not natural?
I think, yeah, that's a good question. So if you generate 6 hand or six finger or 3 finger like that, that is not unnatural in that sense. Yeah, it is unnatural for us, but if it is more look like good quality, so it should not be unnatural. But unnatural, by unnatural, I'm meaning that suppose there are some kind of artifacts which you can see that like suppose here the for example here like you can see that these artifacts are looks like the bloody eye. This is a visible artifact. So in natural images you don't have this kind of bloody eyes. Or there are
Uh,
some images where we can see that we have shown that there are grass where there are some kind of artifacts or unnatural artifacts. So those are unnatural in that sense. Those are not smooth enough or visible artifacts. Uh, 6 finger or 3 fingers are like basically prior based. It is a prior based artifact. Like so we have prior that okay we don't have like 3 or 6 fingers, but it is not unnatural in some sense, I would say.
so it's really not in physics. There's
Yeah,
something
yeah,
natural
yeah, yeah.
law. It's
Mm-hmm.
still it's the training example. If
Mm-hmm.
we have enough patient with a bloody eye to train the model, and you will call it natural, right?
Mm-hmm.
Is that right? Say if I have a lot of patients in the hospital, they have a bloody eye. I train the AI,
Mm-hmm.
and would this loss is normal or not normal?
No, I think if you are saying that if you have like a bloody eye, in that case, it won't be normal in that. Suppose yeah, if you have a data set where all the images have bloody eyes, so that is not this prior won't work there because this is a prior of natural image where you can see in natural image this kind of inconsistency is not there. So that you are saying physics based inconsistency or those things. So we are not like enforcing that here. Here it is a naturalness, basically the how the image should look like, the smoothness, the texture, how it should look like that, more like that. Then uh, yeah, then specific things.
Oh, so you're saying it's not because of the training data, it's because of the detail,
Mhm,
whether the in frequency space, whether they are, comply to the detail of
mhm,
texture.
mhm.
Okay.
Yes, yes, yeah.
Yes.
Because this prior of the naturalness, like kurtosis prior is actually based most on studies from like natural how texture should be there. So in texture, generally there are not very frequent inconsistencies. So if there are inconsistency, we can show okay these are the things which is not normal. So these things that like kurtosis statistics are earlier used to identify if an image is real or fake, natural or fake. So if it is a fake image, then there should be some visible artifacts or visible inconsistencies, which we kind of try to understand if it is a real, natural, or unnatural images. So yeah, that is also one thing which was used it earlier as a motivation.
Okay, thank you.
Cool. Thank you.
And the question on that
Yeah.
bloody eye, it seems to me that it would still classify as a natural image, even though humans would perceive that as a difference from normal, because the bloody eye would still be an organic immersion, or something that happened organic. In other words, I would imagine it should still have the right frequency because it is a natural phenomena. Or am I missing something critical?
Yeah, I think so. If you have to have a natural image or natural, so suppose eye details or something, so it is more natural. So compared to this guide diffusion, if you see that KC and PC, it looks more natural than this, right? So when a suppose when a human to identify, okay, do you see it's natural on what is, suppose if you're given this GD version and GD plus KC plus PC version and ask a observer which you think is more natural. So then he will prefer, okay, this GD plus KC plus PG is more natural, right? So that's how our goal is to make it more natural. So if you have some discontinuity, so to make it more natural in that sense, you can see it is basically doing some locality specific filtering. So for example, this. Mhm.
Aniket, the woman is not natural. She actually has makeup on. In other words, she has eyeliner on, which is not a natural phenomenon, and yet it's part of the database. Or how did this get by?
I think the database actually have a lot of like examples where like women's have this eyeliner and this thing. So that how, but the detail of the eye. So you can see, if you can see that the eye is, so basically here you can see that this is a more bloody eye compared to this eye is look more natural looking eyes, where which has been the model seen or the method generally have seen. So that's the motivation to make it more naturalistic.
So essentially, I think mm, these generative models, they are trying to learn the underlying distribution of the data, whatever that data is. If you're going to talk about only data that's contains, let's say, in case of eye, they do have lots of uh, abnormal eye conditions to us, but that data set on its own has a lot of those samples. Then these generative models, if we let them train on those data, I believe they would pick up on that abnormalness, and for them, it would be something natural. But they may fail in recreating that phenomena. But I think these approaches, they would help the generative model to better replicate that distribution, I think.
Yeah, I think so. Yeah, that's the thing. So that, yeah, I understand. Like they're like so like by natural. So how you define natural, this is one thing. But by natural, I mean, so what is generally people used to see, or images are like distributions are more in domain compared to the out of domain, like that. Does that answer your question, or like?
Yes, my question has been answered. Thank you.
Okay, thank you.
Yeah, I have a second different question. See,
Mhm.
the picture here you show, obviously human will see, you know, there's some improvement. But
Mhm.
say I start from the image, we use, say, Flex, the newest models, some
Mhm.
open source, and the video we use Alibaba's, or when you generate, actually the image or the video are much better than it looks on your paper. So
Mhm.
have you used your, the measurement for the newest open source model to see whether you can tell the difference, whether yours actually can improve?
Yeah. That, so in the paper actually we also compare with the flux model and stuff, but we noticed that when compared to the like this model like GD guided diffusion, which is a bit earlier model, and diffusion models, Compared to that, when it is a newer model, these priors improvements are like less compared to this model, which are visibly you can see much more improvement. But there are like, that's why I'm saying that this is a plug and play method. So basically any model there, it will improve. But if it is already very good quality images model, so the improvement is less compared to the model which is like earlier, or like the quality is not that great. So there the improvement is higher compared to the model which is more like recent, or more like a good quality recently. Yeah, that's also we have not observed, and we also reported in the paper that.
Okay. So, but what about the compute power? The inference for the diffusion model is much higher than the GAN model.
Mhm.
So, with your this kind of improvement, how much compute power it takes?
So this loss function is very easy to use, so that's why it does not require much more, like much computational complexity when you training this model, training this with this loss. It is the uh, overhead is negligible, but when you inference, there is a like two forward pass has to be done, because the perceptual guidance strategy has both unconditional score and unconditional score. When you combine those, it actually im it actually have two forward pass, and that is also not very uncommon, because on cluster free guidance, those model also have two forward pass. So it will have some complexity, but not that huge compared to what the base model is.
Okay, and my last question is,
Mhm.
is there any situation that, if human will see actually your method result will make it worse with the best quality image? Would make it worse, or it always improve? It doesn't matter how much, but as long as it improve, that's maybe we can use it because the compute power is less. But
Mhm.
is there any risk using this? Because otherwise, how do we know it's better? We have to, hire human to see it, right? But if you can guarantee it's better, then why not to use it?
So your question is where this method don't work like that?
Uh, yeah, if it doesn't work, doesn't make it worse, that's okay. But
Mhm.
is there any situation make it worse?
Yeah. I think so. For example, like yes, this is, as I mentioned, this is a prior for natural images. So if you have a image for medical like domain, or like cartoon other domains, so then this prior won't be helpful, because this is not a prior for that. So in that case, I'm not sure how it should not be helpful. Like, yeah. So if you have a medical image, you want to improve the quality of the medical image. So medical image is not natural. So that's how. So in that cases, it might not be useful. Yeah.
Yeah, we are just generating characters, not human, the
Mm-hmm.
natural scenes. So we are not, trying to modify, just want to generate some AI image that looks real. So
Mm-hmm.
you are saying in that situation, it always guaranteed to be to improve and never get worse.
Yeah, in that case, not always like in diffusion model, you can't guarantee, but I'm not saying not I can't claim that it should improve there as well. If you have like total Minecraft, this kind of like a cartoonish generation or something like that, then it is not a good use case for this loss.
Yeah, we're only for human, the
Mhm.
real human and the natural scene. We are social media, we are content generation company, so
Mhm.
we're looking for this kind of solution. But right now, there's a lot of artifact generated, six fingers and others, and also I think the second is our problems character change. You
Mhm.
make it better, the You can say you have a Dr. Roy AI image in my channel today looks this look tomorrow looks more real, better, but you are it's a different person. Then it's not. So does it really make it even make it better, but make it less consistent, characterized? Maybe look different even.
Yeah, I think, yeah, so then that's interesting. Because so I did some another work which is like more this thing like this content generation, style generation, and for that actually it won't be that much helpful, I would say, because it is more good for this kind of task, super resolution, or like uh, few short fine-tuning tasks for natural scenes or nerve and this kind of stuff for that, but not those content creation, those things, it might not be that helpful. Yep.
Okay, thank you.
Thank you. Yeah, maybe just maybe moving forward. So moving forward, I'm gonna explain another work, which is basically the same motivation that improving image quality is challenging. But suppose improving image quality condition on multiple concept or multiple images are even more challenging. So and even more challenging things are to generate combining multiple concepts for few example. For example, suppose if you have a content image and a style image, our goal is to generate a blended output. That is more challenging. And to this end, basically, we propose this work, which I'm going to present next. It's called DuoLoRA, cycle consistent and rank disentangle content style personalization. This is a joint work with Qualcomm AI Research and Hopkins, and it published in ICB like last year. So yeah, a bit of just overview of this work. So the goal here is to join personalization of content and style images. And the challenges here is to, can we like learn jointly content and style from few examples? Because earlier there work on like neural style transfer that will take a lot of examples, but here if you how we can do for fewer examples. And the key novelty in this work that we propose a rank dimensional masking strategy. We use layer priors for content style encoding, and we also use cycle consistency of content and style for better image generation. A bit of background of low rank adapters. So as you guys might already know that low rank adapters are parameter efficient method to fine tune large vision language model or LLMs. And here our whole discussion was how you use the LoRa with respect to stable diffusion X large Excel unit. And the goal is, suppose instead of training the whole unit model, you can just learn the LoRa weights, and that can be useful for training your personalized concept or personalized specific styles. Now in this content, there are some kind of related work. So suppose I have a content. So for example, this case, suppose I have a content image and a low rank adapter, which is low rank adapter across all the SDXL, XDXL, all the layers. So suppose there is a low rank adapter trained for the content images specifically, and a low rank adapter trained for the style images specifically. We call it WC and WS. So how we can combine those efficiently? One very naive approach is to just do naive adapter merging, like naive scaling, which looks very simple, but it won't work that because it have cross concept interference. So there's a recent work called published in ECCB last year, which called like ZipLoRa. What they did, suppose if you have the content load rank adapter and style load rank adapter, and in the output dimension, there are some like learnable mask. You can do one thing, you want to minimize their similarity of this mask, and that's how you are making sure to your concepts are more independent to each other. So that is the concept of ZipLoRa. Basically they are learning mask in the output dimension and make those masks independent to each other this way. So that is a related work. But here our motivation in this work was that the low rank adapter works, all actually work on the same rank. So for example, any complex scene or simple scene, it has to have the same rank, else there will be dimensionality mismatch, and that's how you can't combine those efficiently or anyway. But our motivation here is that for complex scene, we might require higher effective rank to encode the low rank adapter. And for simple scene, we might require lower effective rank to encode the concept. So how we can use, or how we can introduce this rank adaptability in the low rank adapter merging framework, which is that time not there in the literature, and that was our key motivation. So the key motivation here are we provide adaptive rank flexibility while merging LoRas, and since we are dealing with like few short examples and try to merge from few our examples, we try to investigate the diffusion unit layers to understand how the content and styles are encoded in diffusion unit. And additionally, we propose to use cycle consistency between content and style to effectively merge content and style LoRas for better content style generation. So this is the key idea of DuoLoRA paper. So suppose in prior work, what they did, as I already mentioned, so suppose there is a content low rank adapter trained from the content image and this style low rank adapter trained on the style image. They learn mask in the output dimension and make sure those masks are independent to each other. We did a very simple trick which solved multiple problems. So instead of learning the mask in the output dimension, we learn the mask in the rank dimension. So this simple trick solves multiple problems in the sense that it provides adaptive rank flexibility since you are training the mask in the rank space based on your need of the content or the image, you can have adaptive rank flexibility. And this significantly reduces number of trainable parameter, which is more efficient for edge device or deployment on edge. And since we are disentangling in the rank space, we also notice that better content style merging, as you can see from the images. So yeah, this simple trick actually solve multiple problems and multiple benefits. And we theoretically also shown in the paper that running mask in the rank dimension provides better approximation error compared to learning mask in the output dimension. Yeah, do anyone have any questions on this? Yeah, if not, then I just maybe move to the next slide where I'm kind of getting each of the component individually. So in DuoLoRA, basically we have three components. First component we call, as I already mentioned, like moving the mask in the rank dimension, which we call zip rank, that provide significantly less trainable parameter and adaptive rank flexibility. Now, once we have that, then we try to identify in diffusion unit how content and styles are encoded. And our observation is that as you can see, content or concept is a local concept. Like for example, this cat, the cat is a local thing. And if you want to encode the detail of the cat, it has to uh, capture the local details. And for capturing the local details, we find out the innermost diffusion blocks, which have a lower deceptive field, those are more content dominant. Contrary to that, you can see the style is all over the image. So therefore, style is a more like a global details or global concept. And to capture style, like global concept like style, we have identified that the like layers with higher deceptive field, which is mostly in the outermost layer like this. So those are more style dominant block. We have did an experiment to verify this, and it actually shows that the innermost blocks are more content dominant and the outermost blocks are more style dominant. Now, once we identify which are the content dominant block and style dominant block, we provide this explicit rank constraint that if it is a content dominant block, make sure the content merger rank should be higher than the style merger and vice versa for the style dominant block. Now we have noticed that this implicit rank constraint is actually, it actually boils down to a loss function, which is a combination of the sparsity norm and the nuclear norm, because rank constraint optimization problems is actually a nuclear norm minimization problem. So using this, we kind of boil down that the content dominant mergers are trained with this loss, which is a combination of sparsity and nuclear norm. And the later layer, the mergers are trained with this style dominant loss. So this is how we incorporate the layer priors during the merging. And additionally, we also use the cycle consistency. How it works: suppose if you have a content image, we add style details using the style prompt and the style LoRA interrupter. So here you can see in the content image, we are adding the style details, and then we remove the style details with the same style LoRA interrupter and the style prompt, and make sure the reconstructed versions are consistent to the original version. So this is the typical method of cycle consistency, where you add style detail from the content image and remove the style detail and make sure those are consistent. So we call it like L cycle consistency over style, because here we are providing the cycle consistency over the style. Similarly, for the style image, we add content details using the content load interrupter and remove the content details again with the content load interrupter and the content prompts, and make sure those reconstructed versions are consistent to each other, and we call it L cycle consistency loss with respect to content. And now finally we add the cycle consistency across content and style to propose this constyle loss, which is a combination of both. So yeah, this is the overall view of the DuoLoRA. It's just summarize. This has three components. One is zip rank, that learning the mask in the rank dimension. Second, we use the layer priors based on the which layers are more content dominant, which are layers are more style dominant, and use that context while training the mergers. And additionally, we use the cycle consistency, where we add style details and remove style detail and make sure those are consistent to each other. Yeah. Do anyone have any questions on this?
I'm wondering, how did you use the layer priors? Did you explicitly enforce those during training?
Yes. So when enforcing the training, so basically we are learning the mergers across all the layers of the diffusion unit. We identify the innermost layers, so we also have this analysis for each of the models. For those layer, we make sure when those mergers across those layers are trained, we use this either it is content dominant block or style dominant block, and based on that we use specific loss.
I see.
Yeah.
I'm having a problem understanding the style in the picture of the man. I think it's a Van Gogh. I'm guessing, but what exactly is the style? What features are different between the top two pictures of the man in the hat? Is it the orange sort of afternoon colors, or what is the style considered?
Yeah. So the thing is that so here for the two images, so instead
Yes.
of when we are kind of making sure that these are consistent, instead of making sure consistent to the original image, we try to avoid mode collapse, this kind of problems. We also change the style a bit to the style prompt and making sure that those are consistent. So for example, this IS is the style image.
Yes.
We pass it to the style load and character again to make ISS, so that it has some kind of style variation, and then making sure those are consistent instead of like just making consistent to IS. So we noticed that that actually helps to reduce the mode collapse, or because we are training from fewer examples, specifically when we are training from like one example or two examples. In that case, this like ISS or this uh, augmentation is actually helpful.
I understand the palette changes. What on the pictures of the cats? Why did the cat with the added style, the CSC, and became the ICC cat, is not a palette thing. It's actually a morphological. It became thinner. The cat did, and how did it capture that concept of thinner from the two training pictures, I'm assuming, which are the vertical pictures of the cats?
So the thinning, so the picture ICC, which you call C as thinning, so basically it actually captures the content like of the cat. So basically it might have different viewpoint, different variation, so that like it should not be just the cat. It should capture the cat in different viewpoint or different background or different variation, so that it is showing that just that like that. And when you are saying that, okay, in that case, when I add such style detail, make it ICS, there are
Yes.
some style is added. And when I remove the style, it becomes the same cat. And
Yes.
they make sure, okay, this cat and that cat should be similar to each other. And again,
see.
similarly, this is more helpful when you are using very few examples. So we
I
find out
understand.
we can directly use, we can minimize the IC and ICSC, but find out that if we augment with the content loading adapter, so it will add more variation to the image. So that is helpful for few short cases mostly.
Okay, thank you.
Thank you. Yeah. So yeah, then I just go to the experimental results. So we actually compared this method on multiple benchmark, Dream Booth, Style, Subject Blob, Custom 101. And with respect to this kind of metric, Dino similarity is the object, how the objects are retained. Clip image similarity is also object are similar or not. Clip text similarity shows how the prompt adherence are there. And CST is a metric which is to identify how similar the styles are. This is a new metric which is recently proposed, and we tried that metrics as well. And we have seen that across the board, our method DuoLoRA improves upon the metrics across all the benchmark with significantly less number of trainable parameter. For example, with SDXL stable diffusion extra large, there is a 19x less trainable parameter and still better performing better. So that is quite interesting and quite motivating for us. And we also did this user study, with using Amazon Mechanical Turker, which also verifies that humans also prefer DuoLoRA compared to the baselines. And there are some ablations which shows each of the method, each of the components are important for us to get the whole good quality images. Now, here are some qualitative example where we can, this is the basically content and style combination with fewer example, like one example here. And we have seen that DuoLoRA actually captures both the content and style efficiently, where other baselines sometimes miss the content or miss the style or miss both sometime. So DuoLoRA performs better compared to the other baselines. This is the experimental validation. And another thing is also we want to check if when we combine the content and style, does it forget the recontextualization capability of diffusion models? So it actually can capture the diffusion. It can actually do the recontextualization. Basically, it can adhere to the prompt. For example, when the dog in this style sleeping, it shows that its eyes are closed. Nobody has known how the aliens sleep, but hopefully this is kind of okay that the alien is sleeping in this way. And also you can see the alien is driving a car. I don't know if he drives the car like this, it might get a ticket here, but he is not in Earth, so I don't think it doesn't matter. but it
Actually,
shows.
the alien sleeping, someone sleeping across a path in the wood is very unusual.
Yeah, but I think alien sleeping is also like that's not say we haven't seen, but it shows that it's laying down that actually makes the for like actions is like fine.
Yeah,
And
yeah.
also
I'm just saying, like it looks
yeah,
odd. It's like it's dead. rather
yeah,
than-
it's like it's want to commit
Yeah.
like suicide or something, want to trying to run over like that. But yeah, it's kind of interesting to see this stuff like yeah, but it shows that the recontextual capability is also maintained, which is pretty good. And finally, we also did the multi-concept customization. Suppose there is a not only one single concept. Suppose there are this teapot and this dog in this style. So how we do that? So DuoLoRA is not designed for that, but we notice that DuoLoRA can kind of tackle this problem compared to the baselines, where you can see concept mismatch or concept vanishing. Yeah, and so this is the work. Do you have any questions on that? Then maybe I just can go to the next future directions. I think, yeah, should I go to that? Like, so the future directions which of our research could be like, can we do generations with reasoning? Like right now, combining the diffusion models and LLMs to create some generations with reasoning. For example, suppose if I want to generate a prompt like create an image of a capital of India. So it should understand the capital of India means Delhi, what Delhi should look like, what it should contain, something like that. So those things we try to explore next. And also 3D and video generations is also another important and like next step which we can uh, do. Yeah, and for acknowledgement, I would like to acknowledge our wonderful seniors, Piraz and Upal, for inviting me for the talk and giving this opportunity to present my work in front of the everyone. And also IEEE Computer Society, San Diego, and obviously my professor advisor, Ramachalappa, and AIM Lab, Johns Hopkins. Yeah, do you have any questions? I will happy to take that.
How do I contact you? Maybe discuss a little bit more after this, or
Yeah.
this way to communicate. Yeah, I'm in North California. It's Silicon Valley, not San Diego.
I think yeah, I can with in this talk I can send my email ID. So my email ID is basically I can't.
So just one thing, David, do you have access to the announcement for this event? So there's
I
a link,
do.
and contact information of Aniket. But of course, Aniket, you
Oh,
can share your email here in the chat too.
Okay, yeah,
oh,
I can. Yeah, I
I
can.
didn't see that only for the society, right? The local chapter.
I think there's a section where there is Aniket's photo on top of it, where it has its name.
Okay.
There's a link. Yeah,
Oh,
that's
okay.
the LinkedIn profile.
Oh, link.
And
Okay.
actually, he's near Silicon Valley. He's in
Yeah.
Northern
I
California.
am actually Indian. Okay, I'll share in the chat.
Yeah. If you share chat, also I have a LinkedIn. We can link it.
Okay, yeah, sure. Yeah, my LinkedIn. Yeah, I can also.
Yeah, my LinkedIn share, I can share with
Okay,
you.
sure. Yeah. Yeah, I think I just connected you. Yeah.
Oh,
Thank you.
okay. All right.
Thank you so much, Dr.
Thank
Roy.
you.
It has been a great talk. We really enjoyed, and there was a lot of interaction, which we all enjoyed, I believe.
Yeah.
Thank you so much.
Thank you so much. Yeah. Thanks for
Bye.
hosting the talk and like everyone for joining. Thank you.
Yeah. Thank you. Thanks, everyone.